Today we're working with the physical. The initial version of the Learning Tasmota PCB has served us well. With that said, there are some enhancements that we would like to make to this board. For the sake of learning, mastering, and applying, we will do a complete redesign of the board with Easy EDA. Let's get started. Welcome to episode 7 of marktroyer.tech. Unfortunately, it has been a very busy start of 2021 with work. I did not have enough time to complete an episode last week. I will be moving to producing an episode every 2 weeks moving forward. In this episode, we will be redesigning the Learning Tasmota PCB. I suspect this will be done over 3 episodes. Before getting started with this episode, we will do a quick review of the electronic design automation tool that I will be using. It's called Easy EDA. Following this, we will examine the desired changes of the current version of the Learning Tasmota PCB, focusing on both the electronic circuit design and the physical printed board design. We will then complete the electronic design, leaving the PCB layout for the next episode. With that, let's get started by looking at the tool that I've chosen to use for this particular project. The product is called EasyEDA.com, which is owned by JLCPCB.com, a manufacturer of PCBs specialized in prototyping and small batch production. I chose this tool for 5 key reasons. First, there is a very large YouTube community for learning, mastering, and applying with this tool. The product also seems to be very easy to use compared to other PCB design products that I've used in the past. Third, their libraries of parts seems to be extensive. I've been able to find everything that I need in terms of components. It's also purely web-based, not requiring any installation of software nor any plugins. And finally, it's free, as in free beer, free pizza. Can you imagine that? With that, let's talk about some of the design changes that we would like to make to the Learning Tasmota PCB. There are 4 primary changes that we will make. To begin, the current size of the PCB is 50 millimeters by 70 millimeters. This was an arbitrary decision when I initially designed the PCB. For the next version, I would like to extend the size of the PCB so that it fits on a standard low-cost hobby box that can be bought on AliExpress or Banggood for around $1 each. There is a box with an external dimension of 60 by 100 by 25 millimeters that I have purchased over the last few years on multiple occasions for different projects. The idea is that the PCB will replace the top of the box. I've placed a URL of the box down below in the episode notes. The second change is to the temperature sensor that I selected. As Tasmota supports a wide variety of sensor types, I would like to provide through-hole pads that support not only the Dallas Maxim DS18S20, but also the popular DHT and DHT22 temperature and humidity sensors. So one or the other could be used. The idea is that we will provide 2 separate pads that have the data line linked back to the GPIO2 or D4 pin on the Wemos D1 Mini. Looking at the pin out mappings, the Dallas Maxim DS18S20 or the DS18B20 uses 3 pins and the one-wire protocol. Here we see 2 popular form factors for this sensor, the so-called TO92 format and a temperature probe format. The other popular sensor for the temperature and humidity measurement is the DHT11 and the DHT22 sensor. Both of these are nearly identical. Both have 4 pins, 3 of which are used. The DHT22 offers more temperature range, however. The pin layout is identical on both of these and uses a variant of the one-wire protocol. The third change is to the actual pad size of the Dallas Maxim DS18S20. Let's take a look at this under the microscope. On the current board, the space between the pinholes is approximately 1.27 millimeters for each of the 3 pins of the TO92 semiconductor package. While this is very efficient from a PCB board perspective, it is harder to solder for beginners and requires very steady hands. Instead, we will be doubling the spacing to 2.54 millimeters or 100 mil. This is the same spacing of all standard electronic prototyping breadboards. It will require that the pin legs of the TO92 device are slightly widened before inserting into the PCB, as one would have to do with a breadboard. The fourth change is to add a 4.7K ohm pull-up resistor to the data line from the DS18S20 port connected to the 3.3 VCC port. The function of a pull-up resistor is to set the default logical value in a circuit using a relatively high-value resistor. Both of these temperature sensor families use the one-wire protocol for bidirectional serial communication. The pin needs to be pulled up to 3.3 volts by default, which I had not implemented previously. While it seems that Tasmota does account for this in their firmware, it is a loose end that I wanted to clean up in the next build. With these 4 changes in mind, let's go ahead to the computer, to our browser, and go to the website easyeda.com. I have already logged in and have the current circuit design of the version 2 of the Learning Tasmota PC up on the screen. I've saved this version 2 away for good keeping and have now renamed it to version 3. As I mentioned before, this is an electronic representation of the board. I've broken up the design into 6 logical sub-designs. This makes the reading of the design a bit easier. The first and most important sub-design is the actual microprocessor board, the Wemos D1 Mini. As you can see, there are 2 pads of 8 pins on this board. Most of these pins have been connected to logical network ports or nets, which link to the other sub-designs. Network ports or nets allow for easier to read and modular designs in general. On pin D4 or GPIO2, for example, we can see that this links to a network port called DS18S20. This is the data line for the one-wire device. There are also VCC and ground network ports also for the 3.3 regulated power and the ground coming from the Wemos D1 Mini. Turning our attention now over to the temperature humidity area of the circuit subdesign, we can see the DS18S20. We will be replacing this with an alternative DS18S20 component with a wider pad layout. Additionally, we will add a DHT22 sensor and a pull-up resistor. Before we do this, let's space everything out a bit for the other components we will be adding to the subdesign. Okay, let's move the network port connections to the right to start with. And then let's also move the current temperature sensor over to the left. Let's start off by looking for a replacement for the DS18S20. I've mentioned the words DS18S20 and DS18B20. They're more or less the same product, although I think the DS18S20 has a higher level of specification. For this search, we're simply going to look for 18B20. We're looking for a TO92 form factor with a 2.54 millimeter or 100 mil hole spacing. Let's look at a few of these and verify the hole spacing. The first might work, but I need to verify the hole measurements. The second, I believe, is the same that I have now. Let's go click back on the physical layout of the first and see what it looks like as on the PCB. Using the measurement tool, I can see the distance between the pins. Let's look at the distance between the top 2 pins in this case. Indeed, the component seems to have a hole spacing of 2.54 millimeters. Just for grins, let's go back and look at the layout of the other part, which I believe is the current component that we're looking at now, or that we're using now. Okay, so selecting this component and looking at the PCB layout, the pin distance looks a lot less, at least from the grid perspective. Using the measurement tool, we can see that the distance is 1.27 millimeters, and that's not what we want. Let's go back to the previous component. Let's place this component in the box area now and find our next component. For the next component, we will search for DHT22. The first one looks a little dodgy. It has only 3 pins. Let's look at the second one. It looks better, but let's verify the physical hole spacing. For the DHT11 and the DHT22, you should note that again there are 4 pins, only 3 of which are used. I'd like to find a component that has all 4 pins being used simply for stability purposes. Let's look at the PCB layout for this component. And let's check the distance. You'll notice that on this component, the default measurement is in mils and not millimeters. If we look at the hole spacing, we can see that it is 100 mil. That's 1/10 of an inch. Or changing this to millimeters, it is indeed 2.54 millimeters. This component will work, so let's go ahead and place it in the same area on the design. Finally, let's simply copy-paste one of the other through-hole resistors from the design, since we know that all of these have the same and needed physical proper dimensions for the PCB. My recommendation to beginners of PCB design is to double and triple check the components from the library related to the dimension spacing. While having access to all of these components in a library are great, we cannot always depend on some of the open sourcing of the designs. The measurements are not always what we think they're going to be. With all of the new components on the canvas in the temperature humidity area, let's hook it all together. Remember that this is not a PCB layout. This is only the electronic design, so we should not get hung up too much about the placement of the connections, as an example, to be at a 90-degree angle or not. The logical connections are the most important part of the circuit design process at this point. So let's go ahead and hook up all of these together. This is purely a manual process of hooking up all of the lines from the ground, data, and VCC lines. Like I said, I tend to use 90-degree angles for clarity in this part of the process. It is most efficient to make a connection and then go back and then clean up the angles of the actual line in the circuit connection. Let's fast forward through the rest of this. And let's not forget to change the value of this pull-up resistor to 4700 ohms, or 4K7 for short. In principle, the electronic circuit design is now complete. Let's make an attempt at creating a PCB so we can verify if there are no errors in the electronic design. It will ask us if we want to check the nets or network ports, and we will say yes. We can see that there is one warning. The most common errors at this point are dangling network ports or unconnected pins. As I mentioned before, the DHT22 sensor has 4 pins, of which 3 are actually used. The 4th is not connected, as it does nothing but provide some level of physical support. We will attach a no connect or large green X on pin 3 of the DHT22. Okay, let's convert to PCB again and see if it works. Great! Given that the software is now asking us for the desired dimensions of the PCB, everything seems to be okay. Let's just fill in this with a dimension of 100 millimeters by 60 millimeters and press apply. We have now transitioned into the PCB layout phase. We can see the dimensions of our PCB in purple. Additionally, all of the components are in yellow with white pads. The blue lines are the connections between the component pins. These are called rat lines. In the next episode, we will route all of these rat lines using both lines of this 2-layer PCB. So let's go ahead and wrap up. We used a free and easy to use web-based PCB creation tool called easyeda.com. With this tool, we made 4 changes to the design of the Learning Tasmota PCB, which will allow it to be placed on top of the box. It will also allow it to use additional sensors while also making it easier to solder and build. Finally, we verified the design and started the PCB layout phase. In the next episode, we will lay out all of the components on the PCB, manually route all of the connections or rat lines, and ready it for manufacturing by creating so-called Gerber files. These will then be submitted online for manufacturing. I've placed links to the black hobby box and the Easy EDA PCB design tool in the show notes below. If you found this video useful or interesting, please click the like button. Please also consider subscribing to this channel to get a front seat when I release new videos. This is Mark at marktroyer.tech signing off.